Good day, Hojam. I'm Abdullah, and today I will be presenting the introduction, background, and methodology of our project on time-dependent deep image prior, or TD-DIP, for dynamic MRI reconstruction. Dynamic MRI extends conventional MRI by capturing anatomical motion over time, such as cardiac and respiratory motion. However, dynamic MRI suffers from long scan times and motion artifacts. To speed up acquisition, MRI data in case space are commonly undersampled, but this leads to reconstruction artifacts and reduced image quality. Therefore, dynamic MRI reconstruction involves a trade-off between imaging speed and reconstruction quality. Traditional approaches such as compressed sensing and parallel imaging methods like SENS and GRAPPA reconstruct images from undersampled measurements. More recently, supervised deep learning methods using convolutional neural networks, or CNNs, have shown strong performance. However, these methods require large pre-trained datasets and may not generalize well across different imaging settings. Our project focuses on time-dependent deep image prior proposed by you and colleagues. TD-DIP extends the deep image prior framework where the neural network itself acts as an implicit image prior without requiring pre-trained data. Instead of training on large datasets, TD-DIP directly optimizes the network using undersampled measurements from a single MRI scan. The key idea is that neighboring frames in dynamic MRI change smoothly over time due to physiological motion, such as heartbeats or breathing. By exploiting these temporal correlations, TD-DIP reconstructs temporally consistent image sequences. The method works using a forward model, which simulates how MRI measurements are generated from reconstruction images. During optimization, the network generates an image, converts it into simulated case-space measurements, and compares it against the actual measured data. The reconstruction is formulated as an optimization problem, where the objective is to minimize the difference between the measured and reconstructed case-space data. Optimization is performed iteratively using the Adam optimizer. Unlike compressed sensing, TD-DIP does not explicitly impose sparsity constraints. Instead, the neural network architecture itself acts as a regularizer. The network receives latent variables as inputs, which are arranged on structured manifolds, such as lines, circles, or helices. The helical manifold performed best because cardiac motion is approximately periodic over time. TD-DIP also introduces a mapping network, or MapNet, which transforms the latent manifold into a more expressive latent space. This helps the model better capture smooth temporal motion between neighboring frames. For this project, we use the publicly available implementation and dataset provided by you et al. Our group focused on understanding the reconstruction pipeline, running the implementation, and evaluating reconstruction quality using reconstructed images, error maps, PSNR, and SSIM matrix. Overall, TD-DIP demonstrated strong reconstruction quality and improved temporal consistency without requiring large pre-trained datasets, although the method remained computationally expensive and sensitive to optimization parameters. This concludes the introduction, background, and methodology of our project. I will now pass the time over to my teammate, who will be discussing the dataset, experimental setup, and evaluation process.
Now, I will walk you through the data and how we set up the experiments. We used the cardiac scene MRI datasets released with the original TD-DIP code, a fully sampled case-space tensor of 128 by 128 by 23 frames by 32 coils, together with the coil sensitivity maps. Because the data are fully sampled, we use them both as input by retrospectively undersampling and as the ground truth reference. Then, to simulate an accelerated acquisition, we undersampled the cast space along a golden angle radial trajectory with 13 Fibonacci spokes per cardiac frame, roughly a 10-fold acceleration. The non-uniform Fourier transforms are handled by the Python NUFTT library, and the coil sensitivity maps are folded into the forward model in a sense-style multi-coil formulation. The network is the original TD-DIP basic net, a mapping network plus a convolutional generator about 1.37 million parameters optimized from scratch on each individual scan. We reproduced the experiments on two different workstations, an RTX 4060 and RTX 3050, with different PyTorch versions to verify cross-hardware reproducibility and also to maintain speed in our experiments. For evaluation, we compared reconstructed sequence side by side with the ground truth. With zoomed cardiac regions were useful. Quantitatively, we computed PSNR in decibels and SSIM using image. On the magnitude image per frame, average overall 23 frames. Our main run reproduced the paper's receipt. 10,000 ADAM iterations at a learning rate of 10 to the minus 3. We also ran 4 supplementary configurations shown in table, varying the learning rate and iteration count. The goal was to test the method sensitivity and, more importantly, to ask whether shorter optimization can give acceptable quality, since compute time in TDDIP is biggest practical drawback. Now I will hand it to the next speaker.
Thank you. Following up on that question regarding optimization time, I will now walk you through the quantitative and qualitative results of our experiment, followed by a live demonstration and framework in action. On this slide, we can see the visual comparison between the three outputs. The left image is the undersampled image. Because case-based data is highly undersampled, this image contains strong radial streaking and aliasing artifacts. The cardiac structure is still partially visible, but the image quality is poor and anatomical boundaries are not clear. The middle image is the TDDIP reconstruction. Here we can see that the most of the radial streak artifacts are removed, the heart region becomes much clearer, and anatomical structure is recovered much better compared to the undersampled input. The right image is the fully sampled ground truth. This is our reference image because the original dataset was fully sampled. When we compare the reconstruction with ground truth, we can see that the TDDIP produces a visual close result. There are still small differences, but the overall structure and contrast are well preserved. So qualitatively, the TDDIP successfully improves the undersampled image and reconstructs a clearer cardiac MRI frame. Now I will explain the quantitative result of our different runs. As seen on the slide, our baseline run using the recommended 10,000 iterations and learning rate of 10 to the minus 3 achieved a peak PSNR of 29.48 decibels and a peak SSIM of 0.9. This confirms the original paper claims that the network architecture is highly effective at acting as an implicit prior. However, a 10,000 step optimization takes about 5 hours per scan on our hardware. To answer the efficiency questions my teammate just raised, look at our 3,000 iteration test. By stopping early at the same optimal learning rate, we reduce the physical execution time by 70% while maintaining an excellent PSNR of 28.95 and SSIM of 0.9, virtually identical to the baseline. But the model is highly sensitive, as you can see at the bottom of the table, pushing the learning rate too high. 10 to the minus 2 causes optimizer to overshoot the loss minimum, resulting in mathematical divergence and drop in metrics. Before we look at static qualitative image for these failed runs, I would like to step out of the presentation and demonstrate how we actually executed this code and generated our results on our local hardware. To get this older repository running smoothly on our modern RTX 3050 and the 4060 setups, we first had to resolve a few PyTorch and sci-fi deprecation warnings in the source mode, and manually configure FFmpeg in our Ubuntu subsystem, so the network could stitch the output tensors with viable MP4 videos. The code uses the provided TDDIP repository and cardiac sign MRI dataset. The input is undersampled case-based data, and the network is optimized from scratch for the single scan. During optimization, the model generates reconstructed images, applies to the forward MRI model, and compares the simulated case space with measured undersampled case space. In output logs, we track the reconstruction progress using PSNR and SSIM. Let's look at the actual video output of this generated. This is the dynamic reconstruction of the cardiac sign MRI. As I explained it earlier, far left is the highly aliased, in the middle is our reconstruction, on the far is the ground truth. You can clearly see how the network successfully suppresses the undersampling artifacts because of the structural helical manifold we mentioned earlier. The cardiac motion is temporally smooth and consistent, with highly accurate anatomical boundaries compared to the ground truth. To summarize my part, TDDIP gave strong visual and quantitative reconstruction results. The baseline run achieved the best quality, but the 300 3000 iteration run showed that similar quality can be obtained with much lower computation time. However, the method is sensitive to learning rate and iteration count. Now my teammate will discuss the clinical meaning, limitations, and overall conclusion of the method.
Now I will briefly discuss the clinical meaning and limitations of TD-DIP. Clinically, the main benefit of TD-DIP is that it can reconstruct dynamic cardiac MRI images from highly undersampled data. This is important because dynamic MRI normally takes a long time, and long scans can cause patient discomfort and motion artifacts. In our results, TD-DIP reduced the radial streaking and aliasing artifacts in the undersampled image. The reconstructed result was visually close to the fully sampled ground truth. The baseline run achieved 29.48 dB PSNR and 0.9066 SSIM, which shows strong reconstruction quality. Another advantage is that TD-DIP does not need a large pretrained dataset. It optimizes the neural network directly on a single scan. This is useful for medical imaging because collecting large labeled datasets is difficult. Also, it uses temporal information between frames, so the cardiac motion becomes smoother and more consistent. However, TD-DIP has important limitations. The biggest one is the computational cost. The baseline method uses 10,000 ADAM iterations, and the optimization must be repeated for each scan. This makes it too slow for real-time clinical use. The method is also sensitive to hyperparameters. A very low learning rate gives slow convergence, while a very high learning rate can make the reconstruction unstable. In our experiments, the 10 to the power of the -2 learning rate caused divergence and visible artifacts. So PSNR and SSIM are useful, but they are not enough alone. For medical imaging, visual inspection around cardiac structures is still necessary. To conclude, TD-DIP is a promising unsupervised method for the dynamic MRI reconstruction. It can produce high-quality cardiac images without pre-trained data and can reduce undersampling artifacts effectively. But for clinical use, the method still needs faster optimization, better early stopping, and more testing on realistic clinical data. Thank you for listening.